Thank you very much. So thank you for Mika and everyone inviting me to here to talk. And I love Islamic geometric pattern. It has been 2 years almost. In December 2016, I was looking at Instagram and trying to see what is like some picture. And accidentally, I saw some geometric and shape by some artist. And I say, wow, this is look interesting. There is all this line, and people posted multiple pictures. Some picture was only drawing, circle line, and they call it construction line, and then they try to paint it. And I say, what? This is cool. I mean, we as math people, I don't like to classify ourselves this way, but sometimes people say, I am math person, I'm not math person. I don't like this, but there is the other side of the story. Say, I am art person, I am not art person. I always saw myself as never being into art, never drawing a paint. I felt I don't have anything to do that. But after I introduced it to Islamic geometric pattern, I went to Plex, I went to Amazon, I bought a lot of art supplies, and I started painting and I started doing some kind of nice pattern. And most nicely, I have been sending this kind as a gift to my friend, and they love it. They put it in their wall. So from never being doing art, I have been involving actively in art, and this is all because of math. And I believe this is a very strong message we have to send it to people who are don't doing math because they feel math is somehow abstract, is boring, is only elite can do it. But I believe there is another side of math. Not only in lecture you can do it in street, wherever you like it. And hopefully I'm trying to talk about that. So there is a very, very famous location in Spain. It's called Alhambra. This location has been built in around 14th to 15th century by Muslim Moors. And there is a lot of art there, and I'm trying to talk about what kind are there and why this is interesting to mathematician. Before that, I have to talk about symmetry. Okay, so if you look at these two pictures, so what do you mean by symmetry? Basically, in a math way, we say a shape is symmetry if you are doing some kind of transformation, the shape is still same. And we have a different kind of symmetry. These two shapes are finite shape, okay? It's not extended in any direction. Look at the first one, butterfly. We have a kind of symmetry, we call it reflectional symmetry. And if you draw the mirror line here, this side is just same as the other side. And actually, if you put a mirror in here, and then you can recover the other side of the butterfly. And so this is have a mirror symmetry. The second one have a different kind of symmetry. We call it rotational symmetry. And this one have more than one rotational symmetry. And whenever we talk about rotational symmetry, we have to mention what is center of symmetry. And in this cases, here's the center of symmetry. For mirror symmetry, we have a line. So people are very, very familiar to this. And actual symmetry is very, very important in not only in math, it's also for biology. It has been shown that about 99% of animal and planet, they have a kind of bilateral symmetry. This is, we call it bilateral symmetry. And of course, we have other shape and other animal that they have other kind of symmetry like rotational symmetry. This is a starfish, and we call this one, we call it rotational symmetry, but biologists call it radial symmetry. So this is very, very known to us, this kind of symmetry. Something interesting, this is barren swallows. I recently know this fact. This kind of bird living in Europe and American. And the female, those female are living in Europe. When there is a season of mate, they are looking for the male which has most symmetrical tail. So if they have more symmetrical tail, then they will choose it. And some people say, some researchers say, the symmetrical tail, they tell you about these male are good for mating because this means they have a good gene. So, but what is interesting, the American barn swallow, they don't look at the tail. They look at the brightness of chest. So this is interesting too. So what I'm interested to talk about today is not biology. I like to talk about most art, but before doing that, let's talk about symmetry of simple shape, and maybe already most of you know it, but I like to revisit it again. So if you have a square, we like to know how many kind of symmetry do we have. And in this picture, I number it just to know when you do symmetry, what is happening to the corner. And also we have a center just to show what is happening to center too. So this is a simple square, we number it, and this is also finite object because it's not extended in any direction. This is very important. And first we talk about reflectional symmetry. This is a number one symmetry. You are reflecting based on the second diagonal. This is a reflection based on the vertical, and this is main diagonal, and this is the horizontal rotation or horizontal mirror. And I think it's clear. In this one, 1, 3 get fixed. What is rotate is 4 and 2. This one, 1 and 4 will be exchange of position, and 2, 3 are we doing. And similar to this one. Another kind of symmetry related to square is rotational symmetry. So this is, we call it identity, which is you don't nothing. Okay, you are not doing anything, and people outside math maybe see this is interesting, how this is symmetry, but we count it as a kind of symmetry because you have a picture, copy it, and you put it back into its place. So this is a kind of symmetry, and a special kind of symmetry. Now you are rotating 90 degrees in counterclockwise. So one become, when you rotate it, one become here, 2 become here, and like this one. Then again, if you have this one, you rotate it 180 degrees, you get this one, and so on. If you get it 270 degrees, you get this one. And of course, we don't mention the other because it will be repeated. If you do 360, you'll get back to this one. So this is the origin position. So for finite term, for finite object, we have two kinds of symmetry. One of them is rotational symmetry. The second one are reflectional symmetry, which we talk about it. So now we list all the kind of symmetry of a square, which if you count them, it will be 8. 4 of them mirror symmetry, and the other 4, the rest will be reflectional symmetry. Now, one of the questions you can ask is, okay, we have a symmetry. We have 8 kind of symmetry related to square. Can we do arithmetic on symmetry of square in another way? Can we add symmetry? Can we add symmetry? What is happening if you add symmetry? Do you get a new symmetry, or is just the old one? And it turns out, actually, you can add them. But we have to say, what do you mean by add them? So first one, if you have the square, you rotate it 90 degrees. Now you have imposition. Now again, you rotate the other 90 degrees. What do you get? So first time 90 degrees, next another 90 degrees, you'll get 180 degrees. So in this scenario, you are doing 2 rotation by 90 degrees, you get another one. But already we have this one. We have this one in the list. In another way, 2 rotations don't give me a new rotation outside the 8th element. Still, we are in the same set of symmetry we already have. Now looking at this one. Now we do to rotation, let's do something else. Let's do a rotation by 180 degree, and then we do reflection across horizontal line. So what is happening when you rotate it by 180 degree, this is the result, and then I'm trying to rotate it by, reflect it by horizontal line. So 3 become here, 2 become here. Actually, these two will be, position will be interchanged, and this will get 3, will be 2, 3, and this will be 1, 4, this 1, 1. So even the type of symmetry is different, rotational, reflection, you will still get one of the symmetry you already mentioned. Okay, now let's think this one. If you have 270 degree, then you do another 90 degree. What kind of symmetry do we get? So this one will be what? This side. Anyone? Yeah? Okay. And this one will be? 4. Okay, let me go this way, right? This one's? 34. Yeah, and this was the one that we talked about. This is the first one. So actually, we can easily calculate this kind of adding symmetry. Is not hard, and this is where you do it. So if you do this kind of arithmetic on the set of symmetry, you can maybe note some patterns, some observation. And one of them is if you have two symmetry, you add them together, you'll get another symmetry. The second one, which I don't mention it, is adding symmetry as associative, which is mean if you have 3 kind of symmetry, let's say you have a symmetry type A plus B plus C, this will be equal to A plus B plus C. So you can do these 2 first, then you do this one to it, or you can do the first 2 and then do the third one, and we call it associative property. So symmetry of a finite set is associative. And the third one, which I don't talk about it, is every symmetry have another, there is another kind of symmetry associated to one, which we call it the inverse. And the inverse here means you have one symmetry. If you find another symmetry, when you add it to it, it returns you to the original. It returns you to this one, then this symmetry you added will be called inverse. So let me go back one step. You have 270. When you do another symmetry by 90 degree, it returns to the origin. So this symmetry is the inverse of the first one. And vice versa, I believe, in this scenario, you have this one. So actually, mathematicians were able to transfer from symmetry of a square into table, and we call it this group we call dihedral group, D4. They have a symbol for it. And the way we are doing multiplication of number of integer, we can have a multiplication of symmetry of group. And this have been very, very popular in students who take classes in abstract algebra in university or college. So R1 to R3 is the rotation, and S0 to S3 is kind reflection. You have 4 reflection, 4 rotation, each one. And R0 is the identity. So if any kind of object, they have this kind of property observation, this is informal, by the way, we call it a group. And now I want to talk about another kind of group. So as I said before, any kind of symmetry of a shape has these 3 property, we call it a group. And this case was finite group. This shape does not extend in any direction. But now maybe someone asks, what about if I have a shape extend into infinite? Of course, in reality, this is not possible. But in abstract, Who can stop us? We are doing math, okay? So this is Wallpaper Group, and this is, by the way, this is one of the pattern in Alhambra in Spain. So imagine this shape is extended to infinite in each direction. We call it this Wallpaper Group. So what do we mean by Wallpaper Group? Wallpaper Group is you have a shape, you have a two-dimensional shape, okay? And that shape, there is a tile, that tile repeated. This way, that way, this way, that way. So it's just like you have a floor, you look at it, you have a tile, and that tile repeated everywhere, every direction. So this is called Wallpaper Group. We are no more interested in my finite cases because it's boring. Who like finite? Let's go infinite. Who can stop us? So this is a kind of one of the other wallpaper group. This be found in Alhambra. This is on the floor. So whenever you say wallpaper group, people think about wall. But actually, it can be floor too. It can be a mosaic. It can be whatever repeated shape you can see it. The only condition is it should be repeated in both directions, horizontally, vertically, and of course diagonally. If it's only repeated in one direction, it will be called freeze pattern. This is a different kind of group. So if it's only extended this way, then we have called it freeze pattern, which I don't talk about. Maybe someone else one day talk about that. So now here is the fun come. For finite case was boring because we have only two kinds of symmetry, rotational symmetry, reflection symmetry. For infinite case, you have two more kind of symmetry, translation symmetry and glide reflectional symmetry. Translation symmetry, what do we mean by translation? Translation symmetry, so if you have a pattern, you copy that pattern and you translate it to somewhere else. You put it down, the two patterns match over each other. This is called reflection. Sorry, this is called translation. We don't have this in finite set. Why? Because if you have this guy here, and if you translate it to here, then this will not match over it. That's the point of symmetry, should be matching on each other. But for infinite set, if you have something like this, keep going to infinite, and in all that, when you copy it, when you came here, there is another one come sit down over it. So we have translation. The third one is glide reflection. So glide reflection is what? The glide reflection, you reflect it across a mirror line and you move it. It's not only rotation, it's not only reflection. So if I have a paper here, let me see. Let's see, I have a paper here. So let's say this is a mirror line, okay? And imagine this is extended to infinite for every side. Now if I reflect it, and I take it to the other side, and it's matched on it, matched on the original wallpaper. In that case, we call this is glide reflection. We have two more type of new symmetry. We don't have it in finite shape. So what is happening was this. In late 19th century and in early 20th century, two different mathematicians in two different countries, in the same time, they came up with the same idea that any wallpaper group, no matter what they are, it will belong to one kind of 17 kind of wallpaper group. Another way, we only have 17 kind of wallpaper group. And these 17 can be classified based on the type of symmetry. And one of them is Vidorov, is from Russia. The second one is more famous to math people, George Poila, Hungarian. And this one, 1891, and this one, 1920 something. And they came up with the same proof, same idea, different approach, but the same result, only 17 wallpaper group. The reason he came up with this idea because he was mathematician and he was also in the same time geologist and I think always chemist. And he need this kind of study for crystallography. And people in chemistry or crystallography, they learn about wallpaper group. Okay, so imagine this shape is extended to infinite. And imagine this shape, or before that. These four shapes, if you think about it as a finite shape, they are all same group. They are all belong to the same group. I think this is belong to D4. It's just 8 kind. This one have 8 kind of symmetry. This is have 8 kind of symmetry, 8 kind of symmetry, 8 kind of symmetry. So they are same group of symmetry they have. But if this shape is extended to infinite, and again, all of them, they will belong to the different kind of symmetry. So this is one of the facts about that. Now let's talk about Alhambra. So people studying wallpaper group always interested in Alhambra. Why? Because there was a claim. There was a claim about there is all the 17 kind of wallpaper group in that location, which was surprisingly interesting because these kind more Muslim craftsmen, they don't know about something like that, how they came up with all these 17 different kind wallpaper group. Some of them is very complicated. And the answer, maybe they were just curious. Maybe they just want to please their sultan or master. So there was a competition and one of them came with some pattern, the other one tried to do something more sophisticated to challenge the other one. So in 1930, a female PhD student go to Alhambra and make a research and say, there is only 17 kind of wallpaper group. In 50, someone goes there and say, no, there is all the 17 kind, but they don't say where they are. In 80, some famous mathematician from Majid goes say, no, there is actually 17. In 90, someone else goes say, no, there is 14, and this is the 3 missing one. Again, someone else go write a paper, say, no, there is a 17, and here is the 4, or here the 3 missing one. So there was a debate, but all of them agree in two things. First, almost all kind of 17 wallpaper group exist in Alhambra. Second one, maybe some of them missing, but the missing one is a boring one. Those missing are those which have very, very little symmetry, which was interesting. So it looked like they don't being interested in those patterns they have a lowest degree of symmetry. So 17. Let's start discuss some of these kind wallpaper group. Now this is P1, most boring symmetry wallpaper group in the world. Whenever you see wallpaper, you have to ask yourself, what's repeated? What is a tile repeated? In these cases, this is a tile is repeated. So this one, translation, you get this one, down this one, and translate this one, you get all these. So the repeated one is this. Now, look at this part and ask yourself what kind of rotation, what kind of symmetry you have. You don't have a reflection, you don't have a rotation, you don't have a glide reflection. Nothing. Boring. Who would like to do that? Okay, let's go see if this is one of the very famous wallpaper in Alhambra. And when people go to Alhambra, take a selfie with this. So famous. So if you go to Instagram, you will see a lot. This wallpaper is P1. If you take into consideration the color, there is only one kind of symmetry here, translation, nothing else. Very boring. This is P2. P2, again, whenever we have a wallpaper group, you have to ask ourselves a question. What is the repeated one? Anyone can tell me what is the repeated pattern here? What is a tile? Repeated tile? Can this be a repeated tile? No. Why? Because you cannot. Can you get, so if this is a repeated tile, so you can get this tile. You cannot, so you should get this tile by only translation. So let's copy this guy, bring it here. No, we cannot do it. So the repeated tile should be this and this. So if you have these two, if you copy, translate it, you get this. And if translate it, you get this. If you make a translation, you get this. So only this is too necessary to create the whole wallpaper group. Now let's see, what kind of symmetry do we have? Anyone have a clue, idea? Do you think we have a reflection? No, we don't have, right? What kind of symmetry we have? Translation. Translation, so thank you. All of them have a translation. You are right. Okay, something else other than translation. Rotational. By what? 180. This one have a translation. Sorry, all of them, all wallpaper group have a translation. Copy it, put it there, put it back, all we have it. But there is another kind of symmetry here, which is rotation. And here is a center of rotation. If you rotate this guy by 180, this will be sit on here. And it's not only this one, all the pattern will be sitting down on there. Now, again, this is boring. Let's go to, there is the center of rotation. Now, this is a pattern found in Alhambra, maybe because of the age, have been rotten or not nice anymore. But here's the digital creation of the wallpaper again. And I believe you can think about it, this will be, so this will be, or maybe this one will be, or this one will be your tile. And when you rotate this guy around here, you get this. So whenever you see wallpaper group, you can ask question, what kind of wallpaper group this belong to it? And then you play with the rotation and reflection, symmetry, all of it. Now P3, again from the name, this shape have a kind of symmetry. We call it, they have a point, that point have a degree 3 of rotation, which is mean, and this is a point, if you rotate it by 120, you get here, one kind of symmetry. If this one rotated by 240, you get here. And if you rotate it by 360, you get back to itself. So we have 3 kind of symmetry. Nothing else, nothing more. Only this, of course, translation again. Translation always available. Other than translation, we have another 3 kind of rotational symmetry. And something else you have feel it from the picture. If you look at this point, this is the center of rotation. And we have another center of rotation, and they are different. I mean, this one and that one, this one and this one are same. Look at same. But this one, they have a different kind of rotation. We don't have reflection. We don't have a glide reflection, and so on. This is, I think, the first one, but only playing with the color. Change the color, you will be hot. And this is a center of reflection, and this is another center of reflection. So the reason I am bringing a picture, because this is easy to spot the kind of reflection symmetry. But when you go to the pattern, its kind will be, you have to play with it and see, make sense to yourself. This is another kind, P3, which is very old. I don't know even where the source came from, but here's the visual, graphical visual of this P3. This is P4. P4, again, if you want to ask yourself, where is the, well, what is repeated? Anyone can tell me what's the pattern, what is the tile?
I think we need 4 squares together.
4 squares, like this?
Yeah.
Okay, so you are right, because if you take these two, you can create all this row, but you cannot create these two, right? By translation. If you have these two, you translate it, you don't get this. So we need this 3 and this 4. That's one. So this is the first step you are doing whenever you see a wallpaper group in, I don't know, in bathroom floor, in wall, or in a building. You try to find where is a tile, repeated tile. And then whenever you have a repeated tile, you are asking yourself, okay, what is the kind of symmetry of this repeated tile they have? So I'm thinking maybe we have a reflection here. So when you do reflection across this line, this guy cannot become here. So that's not work. Let's do this one. Oh, it's not coming to here. So we don't have any kind of another symmetry. The only thing we have is rotating by 90 degree. You get this, rotating by 180 degree, you get this, 270, this one, 360 itself. So this is called P4 wallpaper group. And this is the example of wallpaper group P4 in Alhambra again. And if you want to see and this is beautiful, how they come up with this idea only by using compass and ruler, the construction. And this is also very interesting fact because they use only Euclidean geometry. Euclidean geometry only allowed to use a compass and ruler. And this is a geometric, this is a computer generated of the same pattern. You can see this location, the center of this, I don't know, they call Khatam of Suleiman, is the center of the rotation. If you rotate 90 degrees, you will get itself. This is another one. I bring this one because I believe this one belong to Yemen, which is very far. I mean, it's an interesting location. This is beautiful. This is different too in some way. So another kind of P4. This is not in Alhambra. This is from Yemen. Now let's go to P6. In P6, again, from the name, we have a point. That point have an order of 6 of symmetry, which is mean if you rotate that point by first 60, then 120, 180, and so on until 360, you get this. Now my question is, where is the center of rotation? Anyone can tell me? Where do you think the center of rotation of here is? Let me give you a hint. There is a two kind of center of rotation. One of them of degree 6, the other one is of degree 3. So one of them only if you rotate it by 120, you get it. But the other one, if you rotate it by multiple of 60, you get it. Okay, let me tell you the order 3. This is the order 3. If you rotate it by 120, you get this. If 240, you get this. 360, you get this. So this point have a degree of rotation 3. And this is it. This is of degree 3. And this one is of degree 6. This one of degree, anyone? Degree 2. Degree 2. So P6 have a point of degree 6 symmetry to symmetry 3 symmetry. But the name came from the highest degree of symmetry, which is 6. Okay, can you tell me what is the repeated tile here? Let me go back here. Yeah? What's the repeated tile? No more square. Something else. What do you think?
It's like a parallelogram.
This one?
A hexagon?
Hexagon?
Yeah.
Hexagon. That's right. I don't know which program you choose it, but so if you pick this one, you cannot create this one by translation, right? And there is something else. If I give a wallpaper group to two different person, okay? One of them say, I found the tile. The second one say, I found the tile too. And we look at them, see which one is smaller. We take the smaller one. Yeah, so that was, this is a repeated one. This is a repeated tile. And and degree 6, degree 3, degree 2. And this is a beautiful pattern there. Look at this. The degree 6 is this one. Now this is more challenge. Let's together find the degree 3, degree 6, degree 2. Here is a degree 6. Anyone can help me find the degree 3 rotation in this shape? I can find degree 2 is easy.
To the left of that star there?
Which one?
Where that star in the middle is, to the left a little bit?
So tell me up or down?
Left. A little more. Right there?
Oh, so it's degree what?
3?
That's right. That's right. If you rotate this around this point 120, you get this. I mean, this one become here, and this one become here, and they are matching over it. So degree 6, degree 3, what about degree 2? Degree 2, which is interesting somehow to me. Anyone? Try. Here's degree 2. There. If you rotate it 180, this corner come here, and this corner come here. So it's it's fun. I mean, just trying to play with the pattern and see where's the symmetry, where's the center of symmetry, where is the line. It's just fun to play with this kind of shape. This is a computer generated of the thing. Now PM. PM, you don't have any rotational symmetry. You don't have any rotational symmetry. But what do you have? You have a mirror symmetry. And they have a nice property, this mirror symmetry. They are parallel to each other. So I'm taking here. So mirror of symmetry, mirror of symmetry, mirror of symmetry, and so on. Keep going, every direction. This rotate will become here, this come here, and so on. And they are parallel. This is a PM. We call it PM. We don't have a glide reflection. We don't have rotation. We don't have other things. This is the example, because some of them, again, have been on the ground and have been destroyed by age. So they have a museum inside Alhambra, and they show all the tile they already have it. This one will be this one, PM, and here's a computer-generated version of the same one. And if you tell me what is the line of symmetry, this is the line of symmetry. We don't have a rotation. If you rotate it, you don't get this one. Now PMM. PMM, you have two things. First one, you have this is line symmetry, and you have this is line symmetry too, mirror symmetry. This is one, this is one, this is one, and this, and all of them are perpendicular to each other. There is another kind of symmetry. Can you tell me what is it? Okay, so the tile is this one. This is a tile. Can you tell me another kind of symmetry they have, PMM, other than reflectional symmetry?
Rotation.
By what?
I'm not sure what you mean.
I mean, how so this guy,
360 degrees?
all 360 is kind of little boring.
Oh, okay.
All of them have 360. This is why we never talk about. But this is good. That's good. But still, we have a rotation. If you rotate this one by 90 degrees, this is cannot become here, right?
Right.
If you rotate it by 180, this become this one. So yeah, we have a rotation by 190. So if you look at that's it. Look, this is point. Have this is the center of rotation of degree 2, 180, and this is a reflection mirror, and they are perpendicular to each other. This is the example of the Alhambra, and this is it. Now I'm trying to speed a little more. Now this is P4M. We have a point. They have ordered for symmetry, which is mean if you rotate it by 90 or multiple of 90 degree, you get the original one. beside that, we have some other kind of symmetry, which is reflection. But all of the reflection lines are in 4 different directions: horizontal, vertical, horizontal, to diagonal. Look like here. And now you have this, you have this. 1, 2, 3, 4. This point have a degree 4 symmetry, but this one have a degree 2. Why? Because if you rotate this by 90, you don't get this. This one will be here, but it will not be fit on it, will not be over it. So this is have a degree 4, degree 2. When you rotate it by 180 around this point, this one come here. Now what do I mean by this? This is interesting. This is new. This line is new. This is glide reflection. If you reflect it across this line, what do you get? This one become here, and this become here. And we have to move with some way. Yeah, okay. So if you rotate it, this become here, this become there. And it will be like this. Now, if I drag it down, it will be fit on this one. That's why we call it glide. So it's 2 steps. First, reflect it. Second, drag it down. And when you do this, it will be sit down over it. And this is why we call it glide reflection. You need to reflect it, then you have to drag it to the one that is matched. This is the shape in Alhambra again. This is a repeated pattern. And some of them is very, very easy to spot it. It's just you see it, but some of them is not that easy. And the line of reflection is easy. 1, 2, 3, 4. What is the center? There is a center. What about glide? This is a glide. This is a glide, and so on. So the complexity of the symmetry is depend on the pattern too. Okay, this is P6M. So we have 2 things. One of them, we have a rotation by multiple of 60. And the second one, we have a reflection in 6 different directions. Let's see. We have, of course, glide 2. This is a center of rotation of degree 6. If you rotate, by 60, if you rotate by 60 around this point, this one come here, this one come here. If you rotate this one by 120, this one come here, and so on. Now, we know the degree of rotation of this point. Now we have also a reflection line. This is 1, 2, 3, 4, 5, 6. 6 different, in each one is different direction. And we have a glide reflection. This is a glide. This is all different one. This is the pattern found in Alhambra that have PM, belong to P6M Wallpaper Group. This is a computer generated one. And by the way, the artist people creating this only compass and ruler right now. If you go to Instagram and write hashtag IGP, Islamic geometric pattern, you see a lot of people creating this kind of art and show you how to construct it. There is a book. There is a big market for it. In 2017, two books have been published about Islamic geometry. So there is a more awareness about this kind of art, and researchers and educators are interested in it. P3, M1, you have the maximum degree of rotation is 3, 120, and the center of rotation lie on the reflection axis. So what do you mean by this? So look at this one: reflection, reflection, reflection. What is the center of rotation? This one, this one, this one. All the rotation center lie down on the reflection mirror line. And this is the one found. I think this one not in Alhambra one. I don't have the picture, and I don't believe this is in Alhambra. There is other picture, I don't see it. Now P3 1M. In the other one, P3M1 and P3 1M, the difference between them is this. In P3M1, the center of rotation lies down on the reflection mirror line. But here, that's not the case. Let's look at it. Maybe, yeah. Look at this. This is a center of rotation, right? Do you have any reflection line here? You don't have it. And that's why this is a different kind of wallpaper group. They call it P31M. It's some weird name, I believe. I don't like it too, but this is not named by a mathematician. Maybe this is why I'm bad. There is another way to name it by a mathematician, which not widely use it. This is why I don't do it. This is my chemistry people studying chemistry using this kind of notation mostly. Okay, so let me try to, this is the P31M. Again, this is found in Alhambra, and this is a geometric, computer-generated picture of this wallpaper group. Very beautiful. P4G. P4G is, you have a rotation of degree 4, which is mean multiple of 90. If you rotated by 90, this came here. You rotated by 180, you get this came here. And you have, and there is something else. All reflection mirror, they are intersecting in 45 degrees. So this one and this one, the angle between them are 45. So all of them, they are intersecting one point, which is a center of rotation of degree 4. And this angle are 45. This is P4G. This is another famous shape in Alhambra. This is computer generated. CM. CM, you don't have a rotation, another boring example. And you don't have a glide. The only thing you have a reflection. What is the reflection? Here we are. Just reflection. If you reflect this guy, you will get this. If you reflect this guy around this line, you get this. Or around this line, you have this one. You have only one reflection. If you have two reflection lines, then it will be different. And you have a glide, you have a glide. If you reflect this one around this line, this become here, and you drag it down, it will be sit down on this side. So we have a glide. And the repeated pattern is this. Not only that, repeated pattern is this, and these two have two glide reflection. And this one is the pattern on the wall. Again, computer generated. CMM, another one. I'm trying to go fast, so if you have any question. CMM, this is have a rotation. They have a rotation of degree 2, 180, which is here, and you have a two line of reflection that meet at center of rotation of degree 2. There is it, center of rotation, reflection, and you have four glide. You have a glide reflection. This one, this one, this one, this one. I believe it's hard for me to find the glide reflection mirror. Maybe it's personal, but I find it's hard because not only you have to make a transition, you have also move it. So it's two-step. This is very, very famous. I have one picture of this. I drew it by hand and I put it on my wall. So proud of it. So maybe you will do it next time. Okay, so this is again, this is PMG. PMG is you have a center of rotation of degree 180. And you have a reflection in one side, and you have a glide reflection too. So this is a reflection, this is a glide. This is the one I found in Alhambra. This is another example of PMG. Very beautiful. I believe this is Iranian. This is not from Alhambra. This is PG. PG, very boring again. You don't have a rotation. You don't have a reflection. You only have glide. Glide translation. I think I have to say glide translation because you do this and you shift it. And this is another example. You can find it on some kind of thing available in Alhambra. This is kind of one of the rare pattern too. This is a PG. PGG. PGG, you have what? You have a degree rotation 180, and you have you don't have a mirror. You don't have a mirror in any way, but you have a two glide. And the glide reflection are in two perpendicular to each other. So one here and one here. Let's see. That's it. One here, one here. And of course, you have a degree 180 rotation. This is one of the pattern. It's dark because the picture don't take it. And this is a geometric generated of this. And we see this one a lot in everywhere. So I'll stop it in very, very soon. But recently I found something interesting. There is some archaeology scientist, archaeology researcher, they study symmetry in culture. And what they get to say is this: different culture have different tastes of symmetry. Some culture like some wallpaper group more than some other culture do. Even they go farther, they say some tribe in Africa, they like some kind of wallpaper group than the other. And this is why after in one of the database online, after analyzing 1,545 pattern, they came to the statistics that 47.8 of the pattern are P4M. So P4M, a lot of rotational, a lot of symmetry you have is belong to this kind one. And if you look at down, fewer symmetry you have, fewer pattern you have. So it looks like they are not interested in those which have lesser degree of symmetry. And the credit for this kind of picture and thing is a couple location. For group theory, I take it from Mathigon. For the tiling, and if you want to look at the different kind tiling, you have to go to tiling search, big database. I don't know how much, couple thousand database. Not only Islamic, also African, Chinese, and other people. They are very good mathematicians and they are very interesting website. Also, if you want to look at the real picture of the photograph of those patterns, you can go to this website by David Wade. David Wade have been publishing a book recently, last year. So this is also a reference if anyone wanted to look at it. I think I'm done. Any question? Sorry if I was too fast. Yes?
So Islamic design has a very distinct appearance. What do you think separates Islamic design from the design of other cultures?
Okay, that's good. One of them is this. So before Islamic, there was design too. But what is happening is in the beginning of Islam, it was prohibited to create a picture of human or animal. So what they needed is this. They tried to decorate all the mosque or holy places. And to do that, they could not picture of human, so they used geometry. And they already translated Euclidean books about elements of geometry. And they have multiple translations. So they use geometry to create sophisticated pattern. One of them is more advanced. If you look at the Chinese, if you look at the African, and compared to Islamic, even in the same time, the Islamic one is more complicated. The reason complex. Why? Because they don't have a choices. They needed to be creative. And the other one is you have seen a lot of star. Look at this. This is a lot of star. Do you see this one? This small, it's called Khatam of Suleiman. Some people claim 50% of Islamic geometric pattern have this shape in it. This small shape. And this Khatam of Suleiman is, even this is the name of one of the Jew prophets, something like that. So, I mean, this is not only all pure Muslim. I mean, just they bring from all the other religion, culture, and they use it. So this is why when you look at the beginning of the Islamic geometric pattern, it's very simple. Even most of them is Christian, came from Christianity and Chinese. But then they developed it, created more sophisticated. Hopefully I answered it, yeah.
Is there any sense of the historical development of patterns? So there's all these different examples of the patterns in Islamic geometry. What came first? Is there any sense of that, or was it something that just seemed to spring all together at once?
Well, what is interesting, it's different. So in Iranian Islamic geometric pattern, it's different flavor, let me say, of Moroccan one. So I think in different regions have a different kind Islamic geometric pattern in terms of the style. And in terms of evolution, I think there is a big evolution. At the beginning, it was very simple. It was it's called four-point star, 5-point star, but then later it will become more sophisticated.
Do you have any sources on that?
There is a paper, it's called Evolution of Islamic Geometric Pattern. I can give it to you. And it listed by shape too. But what is interesting is this. So I don't believe, it was in 9th century or late 8th century, the Islamic geometric pattern started doing it. And till 15th or 16th century, it was highest power of Islamic geometric. When Ottoman Empire come, Islamic geometric pattern no more advanced because the architect, the Ottoman architect, they were not interested in Islamic geometric pattern in general. So that was interesting. This is why when some people say, let's define Islamic geometric pattern, say, okay, all this pattern that available from 9th or 10th century till 15th, 16th century, after that we don't have it. And it declined, to be honest, I believe. Yes?
You mentioned about the Wallpaper Group.
Yes?
Do they have all same elements? And if not, can we classify those 17 Wallpaper Group by looking at the elements?
Yeah, I mean, because this is infinite, so I think we have infinite element. But they have the same generator. So, because in finite shape, if you have this shape, this is finite shape. So you can say, hey, you have 5 symmetry. Okay, good. But whenever you go to this kind of shape, no, they have infinite element. But that's not stopping us. We can find a generator. They have some of them 2 generators, some of them 3 generator. So they classify by generator, I think. And actually, the proof of there's only 17 kind of Islamic geometry is kind of advanced. Even they don't teach it in undergrad. And they use more advanced math, and they use it a generator to show it. Yeah. Yes?
Are you more likely to see these patterns in public social spaces or private?
I think if you go to Turkey, you will see it in the floor. You will see it everywhere.
And in public homes, public?
Yeah, but let me to be honest with you. I believe after you go out from this, you will see Wallpaper Group in a lot of locations.
Well, and I was thinking specifically people creating these patterns in those spaces. What were the people with greater influence would hire artisans to do this, or would people in their homes do it
Oh,
themselves?
okay, so this is a good question. So let me tell you, so there was a time in Islamic geometric, let's call era of creating this, that the artists creating some Islamic geometric pattern, and it was not complicated. It was simple. They could not be advanced because mathematically they would have, this is only skill to create those. And then the collaboration happened between artists and mathematicians. And they gather bi-weekly, bi-monthly, I don't know exactly, but they meet. And the artists ask question, hey, we have a problem. Can you help solve us? Mathematician say yes. In that time, imagine 10th century ago, the mathematician wrote a book for arts, for craftsmen. And from that time, Islamic geometric pattern exploded? So the answer, I believe, no. The answer for this, only those skilled craftsmen were able to create those kind of Islamic geometric pattern. But they created, so the skilled one, they teach some other people to create it at home, yes. But to create the pattern first, it needed some sophisticated math or some math. There's a video they show them how they create it. It's very interesting.
Another question is the effect that it has on the mental state of a person to look at it. It can be mesmerizing, meditative, but also, as you were taking us through it, almost like solving a puzzle. So it can have different effects on the viewer. What was the intent?
That's a good question, and I think so. Your question is this be something to do spiritual? This is a question. This question has been asked. Asked a lot, and there is two directions. Some people say yes, there is some spiritual element because, say, in Muslim people, in some pattern you see there is one big star and everything separated from there. Say this one star is represent God and everything around it, and many researchers say that. To me, when I look at it, I love it, I do, but I don't see a connection. I don't see a connection. But yeah, maybe, I don't know. This question, no one knows. Some people say yes, some people say no. If there is a spiritual element in that wallpaper group, personally, I don't see it, but some other people see it. I think it depends on the eye of person they look at it. I don't know. It's clear? Sorry. Yeah.
So you mentioned your PhD work was in ring theory, and this is obviously group theory.
Yes.
Are different but share similar elements. Did you ever have a moment either messing with this or in your PhD work where you saw connections between the two?
That's a good question, and till that moment is no. And maybe my work is mostly on infinite, and this is another thing is on infinite. And maybe I don't like to do that. Maybe this is kind of my space to enjoy math in a different way. So, to be honest, no. And I don't know, maybe there is, but this is group theory also. Mm-hmm. Group theory is totally kind of other direction from algebra, from ring theory, yeah. Good question, but till now, no. Maybe one day. I was thinking about that because you can create infinite matrices. I'm working with infinite matrices, so you can create infinite matrices, and that infinite matrices consists of 1 and 0, okay? And then you can color it. You see, if I do in Excel that, I say if it's a 1, then make it red. If it's 0, leave it alone. Now, when you look at that from the far, you'll see a pattern. So you can do that, I think, in some way.
Okay, well, thank you very much.